Welcome to our video on cache memory. We are from H4 group. Today we are going to see what is cache memory, why we use cache memory, different levels of cache memory, process flow, cache mapping and its type. What is cache memory? Cache memory is a small, fast memory that is used to store frequently accessed data. It is located between the CPU and the main memory, and it helps to improve the performance of computer by reducing the time it takes to access data. Cache memory is used to store the instructions and data that the CPU is most likely to access next. This means that the CPU does not have to access the main memory as often, which can improve the performance of computer. Why we use cache memory? Cache memory can significantly improve the speed of computer by reducing the time it takes to access data. It can help to improve the overall performance of computer by reducing the number of times the CPU has to access the main memory. It can help to reduce the latency of computer by providing the CPU with the quick access to frequently used data. It can help to increase the efficiency of computer by reducing the amount of time that is wasted on the accessing data from main memory. Overall, cache memory is a valuable tool that can help to improve speed, performance and efficiency of a computer.
Now we are going to see different types of level. The first type of cache memory is known as L1 cache or level 1 cache. In this L1 cache, tiny amount of memory is integrated inside the CPU itself, and all the core inside the CPU have their individual level 1 cache. As the level 1 cache is integrated inside the CPU, they can operate at the same speed as of the CPU, and that is the reason level 1 cache is the fastest among all the caches. Now the typical memory size of the L1 cache is 2 kilobyte up to the 64 kilobyte. Inside this L1 cache there are two types of caches. First is instruction cache and second is data cache. Instruction cache stores all the instructions which are required by the CPU, and the data cache stores the data which is required by the CPU. Now let us see the level 2 cache or L2 cache. This L2 cache could be either inside the CPU or outside the CPU. This cache could be separate from all the cores or shared between all the cores. If this cache is outside the CPU, then it is connected to very high speed bus with the CPU. Memory range of the L2 cache is in the range of 256 kilobyte to 512 kilobyte, but in terms of speed, they are slower than the L1 cache. Now, third kind of level is level 3 cache or L3 cache. All the processors do not have this level 3 cache, but some high-end processor have this L3 cache. And this cache is used to enhance the performance of the L1 cache and L2 cache. This cache is shared among all the cores and it is outside the CPU. The memory size of the level 3 cache is in the range of 1 megabyte to up to the 8 megabyte for high-end processors, but it is slower than the L1 cache and L2 cache. Still, it is faster than the random access memory. Now, let us see the process flow when CPU needs some data. First of all, CPU will look into the L1 cache. If the data is not present in L1 cache, then it will look into the L2 cache, and if the data is not into the L2 cache, then it will look into the L3 cache. If the CPU finds the data inside the cache memory, then it is known as cache hit. But if the data is not available in the cache, then it is known as cache miss. Suppose if data is not available in L3 cache, the CPU will look inside the random access memory or RAM. And still, if it does not find any data inside the RAM, then it will look into the hard disk drive, which is also called as HDD. So when you are starting your computer for the first time or you are opening some application for the first time, then the data will not be available in either cache memory or in RAM. So at this time CPU will get data from hard disk drive. But once the application is open and then after it requires some data, then CPU will get that data from either RAM or cache memory. So this is all about different level of cache memory.
The concept of direct memory mapping in cache memory plays a crucial role in improving computer performance. Cache memory is a high-speed memory component located between the processor and the main memory. Its purpose is to store frequently accessed data and instructions, reducing the time needed to fetch them from the comparatively slower main memory. One popular cache mapping technique is direct memory mapping. In direct memory mapping, each block of the main memory is associated with a specific cache location. The cache is divided into sets, and each set consists of multiple cache lines or slots. Each cache line can hold a fixed amount of data. usually a block of memory. When a memory address needs to be accessed, the cache controller divides it into three parts: the tag, the index, and the offset. The tag is used to identify the specific block of memory in the main memory. The index determines which set in the cache the block begins, and the offset specifies the position of the data within the block. To retrieve data using the direct memory mapping method, the cache controller first checks the corresponding cache set determined by the index. It then compares the tag value associated with the memory address to the stored tag values within the cache set. If a match is found, it is considered a cache hit, and the data is fetched directly from the cache, avoiding the need to access the slow main memory. However, if the tag value does not match, it is a cache miss. In this case, the cache must be updated with the new block of memory from the main memory, replacing the existing block in the cache set. The cache controller makes room for the new data by following a predefined replacement algorithm, such as the least recently used, also known as the LRU strategy. Direct memory mapping offers simplicity and ease of implementation, making it a popular choice for cache memory in many computer systems. However, it has limitations. Since each memory block has a fixed location in the cache, conflicts may occur when multiple memory blocks map to the same cache set, leading to increased cache misses. This phenomenon is known as cache trashing. However, it provides fast access to frequently used data, but it may lead to cache conflicts in certain scenarios.
The second type of cache memory mapping is fully associative cache memory. This cache is most flexible cache architecture. It is a technique that refers to cache mapping that allows mapping of the main memory block to a freely available cache line. Also, a fully associative cache would permit the storage of data in any cache block. There would be no forcing of every memory address into a single particular block. Now let us assume there is a RAM of 128 words along with a cache of 16 words. Here the cache and the main memory are divided into lines and blocks respectively. Every block line is of 4 words. It is shown in the diagram given as follows. Since the main memory has a size of 128 words, a total of 7 bits would be used for representing the main memory. Thus, the physical address would be of 7 bits in size. Given below is an example of fully associative mapping of W24 of the B6. Since the block offset represents the block size, 4 words of a block could be represented through 2 bits. Since the block number represents the block in the main memory, there are total 32 blocks in the main memory. Thus, 5 bit would be required here to represent 32 blocks. We do not need to divide block number into line numbers and tags. It is because in any cache line, any main memory block can come. Thus, block number is our tag. A tag represents the block number as a 32 block main memory. Also, any block can come in a cache line. This is how a fully associative cache memory system works.
Now the next topic is case set associative mapping. This is the third type of mapping in cache memory mapping. Set mapping is the most widely used set mapping as it gives us the advantage of reduced cache conflicts and improved hit rate. It combines the aspect of both direct and fully associative mapping. Now, in set associative mapping, each memory block from main memory can be mapped to a specific set within the cache, and within each set, there are multiple cache blocks available for fetching the data. Now, for example, let's consider a 16 bits cache. You can understand the example better with the diagram. Let's consider a 16 bits cache which has a 4 bit in one level, which means that there would be 4 level. And let's take an example of two-way set associative mapping. You can easily find the number of sets by dividing the number of lines and k. K here is the constant where in k set associative mapping. Now you can actually see one here sets two sets, one in white and one in blue. Now therefore two sets will be formed. Then you Then when you fetch a memory from main memory, use the concept of direct mapping of k mod n, where n equals to number of set. The block will be put in respective set in any line. If one of the tags matches, it indicates a cache hit and the corresponding cache line is selected. Therefore, this process will be complete. Thank you.